bulk of the fluid through this thin film. Let's read the problem. This is the figure for same problem. So we have this droplet. This is the gas film around this droplet in film. The temperature everywhere is constant for this problem. And this diffusion to hypothetical spherical stagnant gas film surrounding the droplet of liquid A. So inner radius is R1, outer radius is R2. Yeah, before starting this problem, so we'll just revise what we have done till now. So this is what all the cases summarized. So what we have done till now. So in first problem, what we have discussed, here we have liquid A and it is diffusing in a gas stream which is having A and B. If concentration of A in this gas stream is given, so we can establish the concentration profile in this region. How come? Concentration will vary from Z equals to Z1 to Z equals to Z2. Also, we can get a flux profile also. But there is no reaction, nothing is happening here. Just A is evaporating and mixing with stream. This was the first case. And then second case, so this case and this case are exactly similar, only there is a notification difference. Okay, so instead of having origin here, we can select the origin here. So one and same thing, exactly same equation we will take here. So here, so Z equals to Z1 equals to 0 and Z equals to Z2 equals to L. This is what we have discussed second case. So exactly same equation we will get, only instead of this Z1, you will get a 0. Instead of Z2 minus Z1, you will get L. Z2 minus Z1, wherever you will have Z2 minus Z1, you will get L. So this was the second case. Third case, we have discussed a three-component system. This is the three-component system. Here, water is evaporating continuously. Water is evaporating in the gas stream of water, nitrogen, and oxygen. Water, nitrogen, and oxygen. If say diffusivity of water in nitrogen, so this is 1 is water and 2 is nitrogen. 1 is water and 3 is oxygen. If diffusivity of water in nitrogen is equals to diffusivity of water in oxygen, then this can be taken as a two-component system. Okay, two-component system. There we can handle as water as a component and air as another component B, which will consist of nitrogen and oxygen, but they don't have any difference as far as mass transfer of water is concerned. Then this case is exactly similar to this. So two component system. This was the case we have discussed. Okay, so if this is the case, then this can be handled just using this as a one component by, and this is one component nitrogen plus oxygen air, and one component will be water. So A will be a component A, water will be the component A, and air will be the component B. So this can be handled. So these three problems, this problem, and this problem are exactly similar, same problem, only some assumptions. Then real problems comes when, say, if diffusivity of water in nitrogen is not equals to diffusivity of water in oxygen, then how to handle the problem? So here also same thing. So we have seen two ways to handle the problem. First of all, we can get that effective diffusivity using a diffusivity of water in nitrogen and diffusivity of water in oxygen. We can get effective diffusivity, and here instead of diffusivity I will be using effective diffusivity. Then this problem is similar to this problem, approximating. This problem can be approximated to these three problems by using the effective diffusivity instead of individual diffusivity of water in nitrogen and individual diffusivity of water in oxygen. This is what we have discussed. Or we can treat it separately also. For that, what we have used is, we have used a flux of nitrogen also, flux of oxygen also. These are the two factors we have used. And one more additional condition we have used, a summation of all mole fraction will be equals to 1. So using these three factors, first of all, flux of nitrogen, flux of oxygen, and flux of water, combining all these three information, and secondly, a mole fraction of water, mole fraction of nitrogen, and mole fraction of oxygen, that summation of mole fraction will be 1. Using that, we can have the concentration profile for water for different value of diffusivity, as well as flux profile also we can get using these. Actually, for that we can use trial and error. This was a fifth case we have discussed. Then after that we have discussed, if now everywhere we are assuming this water level or this liquid level is constant, it is not changing during the evaporation. During evaporation it is not changing. If that is changing, how to handle the problem? That is what we have discussed at the end of the yesterday's class. How to handle this? So we have calculated the rate of change of height and correlated with this rate of this Z1t minus Z10 h of t, or this Z dz by dt. This will be a rate of change of height multiplied by a cross-sectional area S. Say this is the cross-sectional area S. That will give you a volumetric change. How much volume is evaporated, multiplied by density divided by molecular mass. That will give me a molar rate of evaporation, and that will be correlated with a flux equation which we have got from this equation, considering quasi-steady state. Considering quasi-steady state means we can assume a small differential amount of time during which there is no change in height. During which there is no change in height. If there is no change in height means this is similar to this, and I can get same flux profile. That using that flux profile and surface area, I can get rate, and then integrating that equation, we got how to monitor variation of height with respect to time. This is what last slide we have seen actually, and then we have solved the problem. This is what I was telling actually, variation of height with respect to time. All other things are constant. And then we have solved couple of problems based on different density and everything. So anybody has any difficulty in this? Okay, then now today we will be discussing this problem. So here we will have this liquid droplet. This liquid droplet having a radius R1. This is my liquid droplet. Okay, this is my liquid droplet with radius R1. This is what radius of liquid droplet. And it is surrounded by some thin film. This is hypothetical. Okay, and this we have studied this in interface transport flux also. This to compare experimental observation with theoretical observation, there are so many assumptions. So similarly, this hypothetical film is considered around this droplet, and it is assumed that overall resistance to mass transfer is taking place in this film only. There is no resistance to mass transfer after this. It means that bulk of concentration is constant. Okay, bulk of concentration is constant. The gas is flowing over this, and the temperature in this film is constant. Temperature in this film is constant. So consider a system as shown in figure, in which a liquid A is evaporating into gas B. Okay, liquid A is evaporating into gas B, or liquid A is evaporating into mixture of gas AB, which will have A also. We imagine there is some device to maintain the diameter of liquid droplet constant. Here also, initially, to avoid the complexity of moving quantity problem, first case we are assuming liquid droplet diameter is constant. Liquid droplet diameter is constant. It is observed for such a case, overall resistance to mass transfer in a thin film around the droplet. So overall resistance to mass transfer will be in thin film around the droplet. Here the layer of this layer, here the layer with inner, here in this problem, what is that thin film? It will be layer with inner radius R1 and outer radius R2. So overall resistance to mass transfer is taking place in this. So this will be a droplet, liquid droplet. So this will be interface, gas liquid interface, and this is thin film, stagnant film, where overall resistance to mass transfer is taking place. And hereafter there is a bulk of fluid. Bulk of fluid means thereafter there will not be any change in concentration. Concentration remains same. A stream of gas mixture AB, concentration is XA2. It means that a concentration of A in a stream is XA2. So whatever gas is flowing here, in bulk of the fluid, concentration of A is XA2. So mole fraction of A in bulk of the gas is XA2. So this is what given. Flow slowly past the resistive gas film thickness. Okay, to maintain the mole fraction XA2 for R equals to R2. So this will be continuously passing through. The entire system is kept at constant temperature and pressure. The gas A and B are assumed to be ideal. If mixture of A and B forms ideal gas mixture and the solubility of B in A is negligible, derive the expression for concentration profile. So this here we will have liquid droplet. Here concentration is XA2. What will be concentration at interface? Roll number 61, Utvik.
Yes, sir.
What will be the concentration of A at the interface here?
I think it will be XA2, sir.
Huh?
XA2.
XA2 here.
At the interface, na, sir? Sir, can you please repeat the concentration?
What is the concentration of air at this interface? Can you see my cursor?
Yes, sir. I can see your cursor.
So what is the concentration of A at this interface?
Sir, it will be XA1.
XA1. How to calculate this XA1? How to get this value of XA1?
Yes, sir.
Roll number 60, Aditya.
Yes. Yes, sir.
How to calculate the concentration XA1 at the interface between gas liquid?
Sir, using Raoult's law, saturation pressure.
Yeah?
Using using saturation pressure.
Yeah, using saturation pressure. So what will be the exact equation, Aditya?
Sir, P sat by RT.
Not P sat by RT. It will give you concentration. I'm asking about the mole fraction now. XA1 mole fraction. Here we are dealing with mole fraction because because in Fick's law of diffusion and total flux also we are dealing that equation with
Okay.
the mole fraction. How to get a mole fraction at the interface?
Sir, a total pressure by PA.
Total pressure by PA or
Oh,
PA by
sorry,
total pressure?
PA by total pressure, sir,
P
for mouth vacuum.
saturated divided
P
by total
satu
pressure. So
total
this
pressure.
concentration I can calculate. This concentration I can calculate. This concentration is given XA2. So certainly I can get the concentration profile in this gas film. So this is my region of interest, where I want to get the concentration profile, how concentration is changing from this point to this point. That is what overall discussion is all about. Based on this, I can discuss what will be the rate of evaporation of this liquid droplet in this fluid. If I get a flux here, that will give me a rate of evaporation of this liquid droplet. Okay. So Devang Joshi 58.
Yes, sir.
So how to start this problem?
So, first we'll take a differential cell as the concentration is varying.
So
So we will
differential
take
shell is second, third step. You first, before that, what you will do?
sir, first coordinate system.
Yeah, coordinate system. Which coordinate system you will be using?
Spherical coordinate system.
Yeah,
Sir, radial coordinate system. Like
radial
spherical
coordinate.
spherical coordinate system.
Spherical coordinate system. So there is no option for origin. Origin will be at the center. So then you will discuss about variation of concentration in mass transfer. You will discuss about variation of concentration. Here temperature is given constant. Throughout this film, temperature is T1. So this temperature is T1 throughout. So we'll discuss a variation of concentration. Devang, yeah, Devang.
Yes, sir.
Can you explain? So concentration, what are the three directions in spherical coordinate system?
Sir, R, theta, and phi. So the concentration should vary in R direction only.
Only. Why it is not varying in theta and phi direction?
Because of symmetricity.
Because of symmetry. Problem is symmetric around theta and around phi. Hence, there is no variation of concentration in theta direction and phi direction. And as I discussed, here we'll have solubility concentration. Certainly, this concentration will be lesser than this concentration. I am moving in R direction. There will be variation in R direction only. Here, roll number 57, Aman.
Yes, sir.
So, what will be the dimensions of differential shell?
Delta R, sir.
Delta R and theta.
Yes, sir. Delta R, theta, phi Z.
Delta R, theta, phi.
Phi
These will
Z.
be dimensions of differential shell.
Yes, sir.
Whether you are looking this spherical coordinate problem first time in transport phenomena.
No, sir.
So this will be the dimensions of differential shell.
Yes, sir.
What will be boundaries of theta and what will be boundaries of this thing actually? I. Yeah, roll number 56.
So 0 to 2 pi, sir.
Yeah, 0 to 2 pi and 0 to pi. So how exactly this differential shell will look like? It will look like a hollow ball.
Yes, sir.
It will look like a hollow ball. If you remember, so this exactly same problem we have solved in heat transfer. Okay, this is heat transfer. You can think of this aluminum cladding. Okay, this aluminum cladding where there is no heat generation. Some flux will be there and flux will be there. So this, if you just see this problem, so coordinate system is spherical. Instead of temperature, here we are discussing concentration. This is what a spherical shell will look like. Here also, in this problem also, spherical shell will look like in similar, because here also concentration is varying in only R direction, their temperature was varying only in R direction. So temperature is similar to concentration. Temperature in heat transfer is similar to concentration in mass transfer. So exactly similar to this. Okay. So here, so what you will do then next? What is next? 56, roll number 56, Jitendra.
Hello, sir.
What should be done next? How to get rate of mass coming in a differential cell, rate of mass going out of differential cell, plus generation minus consumption equals to 0. This is overall mass transfer equation. What is how to get rate of mass transfer coming in my differential cell?
By the flux.
Flux, a total flux. Total flux will be a NAR. NAR multiplied by
R square. Area.
what is that area?
Surface area.
What is that surface area? What will be the inner surface area of this spherical shell?
4 pi R1 square.
4 pi
R1 square. But for
R1. 4 pi R1.
but sir, for differential cell it will be 4 pi R square.
4 pi
R square.
R square estimated at R.
Yes, sir.
Okay, 4 pi R square estimated at R. And what will be the rate of flux, rate of A going out of differential shell? It will be 4 pi R square NAR estimated at R plus delta R. Again, you can go back to same problem actually, this problem actually. This is the problem. Okay, if you see here what we have done. So this was a differential shell. So this is the flux estimated at R multiplied by surface area, flux estimated at R plus delta R multiplied by this surface area. So just you can see this will be you can think of this generation and consumption. So rate of coming in, going out. So this is what we have done, 4 pi R square. So this is what, so instead of QR, there it will be NAZ, NAR, flux of A in R direction. So flux of A and A in R direction estimated at R. Similarly, flux of A estimated at R plus delta R. That will be equals to 4 pi R square NAR at R plus delta R. And here, so there will be no generation and consumption. So this will be equals to 0. And this is what same steps will be there. Same step, exactly same step. And you will be getting identical equation. This will be the differential equation d by dr of R square. This is flux. And why we are not changing the location of R? Yeah, roll number 53, Shivam.
Hello,
Yeah,
am I audible, sir?
yeah, you are audible. Why we are not changing the location of R?
Sir, the R depends on the radius of the differential cell, like from R1 to
R
R2.
is a function of R. Okay, R is a function
sir.
of R. So hence it depends upon this differential. Hence R we are not changing. So what is the expected equation you will get in mass transfer? Shivam?
Yes, sir. So we will get d by dr of R square into NAR equal to 0, as there is no mass transfer generation.
So now you can think, even though we are dealing first problem in spherical coordinate system in mass transfer, but there are so many fundamental which is similar to heat transfer and mass transfer. That is why we have discussed initially similarity between heat transfer, mass transfer and momentum transfer. Now, even if you know that this QR is similar to NAR in mass transfer, So without thinking anything, we can write a differential equation, okay? Because all the steps will be similar. There, momentum flux will be replaced by mass flux, will be replaced by heat flux. Temperature will be replaced by concentration, will be replaced by velocity. Here, instead of concentration C, we are using mole fraction. Okay, mole fraction. So otherwise, it is no different. These three areas are no different. And as I told initially, also there are some areas where you cannot have similarities, like you can say radiative heat transfer. Whatever be the heat transfer taking place because of radiation, that type of fundamental is not there in momentum transfer and mass transfer. Similarly, in mass transfer, we will not consider only molecular flux. We will not consider only this conductive flux. All the time in mass transfer, it will be associated with a convective flux. Okay, it will be associated with a convective flux. So just try to get the differential equation. Everybody please do all the steps and get the differential equation for this case. So this will be the differential equation we will be getting. So how many of you are getting this equation or have an idea to get this equation? You can write in chat box. If you are getting this equation, just write in chat box. So d by dr of n square, r square, NAR, flux of A in R direction, that will be equals to 0. So anybody is getting this equation? Anybody not getting this equation? Very easy. So intentionally, I have compared this with heat transfer so that you will still get a feeling that, okay, otherwise you will see that, you will say that, okay, shell balance in heat transfer is totally different than shell balance in mass transfer. So altogether, whenever we were discussing shell balance for momentum transfer, that is for heat mass transfer, momentum transfer also, and heat transfer altogether. So you can think of, we have not covered only a couple of classes on shell balance on mass transfer. It is all together from the class where we have started a shell balance for momentum transfer. All that fundamentals can be used here also. Okay, so hereafter, we'll be substituting definition of NAR. So NAR, again here we will have binary system, and solubility of B in A is 0 for binary system. So this for binary system, this already we have discussed. Okay, so when NBR equals to NBR, a flux of B in R direction equals to 0. Why that will be 0? Because a solubility of B in A is negligible. So gas B is not coming in the negative R direction. Okay, NBR will be equals to 0, NBR equals to 0, and using the NAR for binary system, so we'll get this NAR. This will have C DAB dXA by dr is, so this only this term is a molecular flux which is given by fixed law of diffusion. Only this term C into DAB dXA by dr is a fixed law of diffusion, and we will have convective flux also. Convective flux will be equals to mole fraction into NAR plus NBR. Again, NBR equals to 0. So rearranging the equation, we will get this equation. Now substitute this equation in this equation and rearrange, integrate this equation. This is what you will get integrating this equation twice. Integrating this equation twice and substituting the boundary condition. Integrate this equation twice and substitute the boundary condition and get the flux profile in this format. Okay. At R equals to R1, XA will be equals to XA1. At R equals to R2, XA will be equals to XA2. So XA1 can be estimated. XA1 can be estimated by using saturation. Saturation, assuming that at interface the gas layer will be saturated with liquid, and using saturation pressure P saturated divided by RT, P saturated divided by total pressure P, you will get XA1 and XA2 can be given. If XA2 given, or you can measure XA2 is the bulk concentration of A in a gas film actually, bulk of the gas film. So integrate this equation twice and just rearrange the equation in this format. Rearrange the equation in this format and try to get this numerator, not numerator, this power term actually. Question. So integrate this equation twice and substitute this boundary condition. And get this concentration profile. So anybody is having any difficulty or any confusion how to get this concentration profile? Here roll number 71, Imani. Roll number 71. Roll number 70, Abhijit.
Hello, sir.
Abhijit. Any difficulty?
No, sir, actually.
So what is your equation after integrating the equation twice? What is your equation?
So I'm doing it, sir.
Do it fast. Don't have infinite time. Now this, we have already integrated this equation actually. There is R square is also there. Otherwise, similar integration we are done, and integration you are roll number 68, Mitu. Roll number 67, Mayank. Am I audible?
Yes, sir. Yes, sir. Hello.
Mayank.
Yes, sir.
Can you give me the equation after integration with constant? Just whatever be the what will be the first integration of this equation? What will be the
R-
first equation?
R cube by 3 CDAB upon 1 minus XA dXA upon dr.
How come? First integration it will be R square C. This equals to constant C.
D by D.
Okay, this whole term will be equals to C1. That will be first integration.
Yes, sir.
Yeah, anybody got the equation? Anybody in a class? So let okay, I don't know. You people are doing intensively or you are not capable of doing this. Okay, this is what equation you will get. 1 minus XA, 1 minus XA1 that will be equals to 1 upon 1 minus XA2, 1 minus XA1. That will be equals to 1 upon R1 minus 1 upon R divided by 1 upon R1 minus 1 upon R2. So after substituting all these, okay, and there will be ln term also in this. No, ln term will not be there. Okay, substituting all substitution properly and rearranging the equation. What is this equation? This equation is giving me a variation of XA with R, XA with R with a given value of XA1 and XA2 at R1 and R2. So this is the concentration profile when temperature is constant. When temperature is not constant, so this is with the temperature constant. So what will be the differences if temperature is not constant? So here I will have temperature T1 and say T2. T2 is different than T1, okay, which is directly proportional to radius. Okay, R2 divided by R1 raised to n. If T2, so if say now this is simultaneous heat and mass transfer. There is a variation of temperature also, there is a variation of concentration also. So initially we'll go in heat transfer, derive the equation for temperature profile. So temperature profile, once we get a temperature profile, that will be substituted in flux mass profile and you will get. So if temperature profile is given, say here I have a temperature T1 and here I have temperature T2. So how to handle the problem? So first part will be same, okay, because temperature is varying in R direction. So differential shell will be a delta R, theta varies from 0 to pi and phi varies from 0 to 2 pi. This will be same. So it will be like a hollow tennis ball. Differential shell will be a hollow tennis ball and you will be getting same flux profile. Okay, you will be getting same. So as this temperature is varying, first of all, this diffusivity will also vary. Okay, this temperature is a function of R. Temperature is a function of R. So diffusivity will also vary with the temperature. Okay, diffusivity will vary with temperature. It means that diffusivity is also function of R. Okay, here the problem is same. Here temperature is function of R. Similarly, a diffusivity is a function of temperature. This is well known fact. Diffusivity depends upon temperature raised to 3 by 2. And this is temperature profile. This is the temperature profile. As temperature is varying, diffusivity is also varying. What it means that diffusivity is not constant from here to here. Okay, diffusivity is not constant from here to here. Diffusivity is changing. So diffusivity is changing. So I cannot take it as a constant value. And it depends upon temperature, and temperature depends upon R. Similarly, as temperature is changing, concentration is also changing. Okay, total concentration is also function of temperature. Okay, total concentration is also function of temperature because ideal gas law, pressure, if temperature is changing, means pressure will also change. Okay, so that everything you need to take into account. Okay, so otherwise this problem is same. Only the temperature is varying. As temperature is varying, diffusivity is varying. How to account for this? Till this point, this will be exactly same. Till this point, this will be exactly same. It will change from here. Now, after substituting this, previous and this, you need to substitute temperature profile. You need to substitute temperature profile. You need to substitute a diffusivity variation with respect to temperature. Diffusivity variation with respect to temperature, and this is the total concentration. You can see total concentration also depends upon temperature. So this is also function of R. This is also function of R. Okay, this is also function of R. This is also function of R. So you can see this is also function of R. This is also function of R. So accordingly, you will be selecting and then you will be integrating the equation. This is the function of R. This is the function of R. You need to substitute this C and DAB in terms of R. First of all, you need to substitute this C and DAB in terms of R and then integrate this equation appropriately. Because total, as temperature is changing with respect to R, this total concentration is also function of R. this DAB is also function of R. So you cannot take this as a constant as we have done in previous case. As we have done in previous case, this can be taken out directly, and that this R square divided by 1 minus x dx by dr equals to 0. But in this case, this concentration is also function of R. This diffusivity is also function of R, because temperature is a function of R. Temperature is changing with respect to R in gas film with this temperature profile. With this temperature profile, this is the temperature profile. Temperature is changing with respect to R, and diffusivity depends upon temperature, concentration depends upon temperature. Hence, this diffusivity is also function of R, and this concentration is also function of R. Now we will see how to handle this problem. So substituting everything, okay, substituting this DAB at constant temperature T1. This is the, say you can base value. This substituting this, and say you can substitute this C concentration at some reference temperature T1. Substituting this, you will be getting this actually. First, you substitute everything here, C and DAB, and see whether you can get this equation. So try to get this equation by combining all these three equations. Temperature is function of R, diffusivity is function of temperature, concentration is a function of temperature. Substitute concentration in terms of temperature and this temperature with respect to reference temperature. So substitute it here. Similarly, this diffusivity is a function of temperature and temperature is a function of R. Substitute it here, so you will be getting this equation actually. Now you can see this pressure. This is total pressure. This is DAB at temperature T1. This is also constant, and this R is also constant. T1 is also constant. So this term is constant. This term is constant. So because of variation of temperature in R direction, this term will get added here. Yeah, anybody getting this equation? From this equation, substitute C equals to P by RT, and T will be equals to R divided by R1 raised to N into T1. Similarly, DAB equals to T divided by T1 raised to 3 by 2 into DAB1. T equals to T equals to R divided by R1 raised to N into T1. So substitute this here and you should be able to get this equation. Anybody getting this equation? Okay, roll number 29 got this equation. Yeah, roll number 29. Number 29, Vedant. Roll number 29, Vedant.
Am I audible, sir? Hello?
Yeah, you are audible, but your audio is very low. Did you got this equation?
Sir, I got the equation.
Okay, very good. So can you just show to everybody in, can you switch on your video and show your notes, all the steps?
Sir, actually, I didn't write it very methodically, but I have done it.
Oh,
Just a second. Is it visible, sir?
Not all the steps. Can you just show it again?
Yes, sir. Like,
Written nothing actually. Okay.
actually, I didn't do it very methodically. I just took the inside terms and simplified them and did it.
So as I told, C equals to P by RT and T equals to R divided by R1 raised to N into T1. T equals to. that you can substitute. Similarly, DAB equals to T divided by T1 raised to 3 by 2 into DAB1. DAB equals to, and this T equals to R divided by R1 raised to N into T1. You substitute this everything, you should be able to get this equation. Anybody else got this equation? Okay. Okay. Very good. Some people are doing and getting this equation. So now hereafter it is same thing. Now this is constant, this is constant, this is constant, this is constant. Everything is constant. You can take it out, this constant, and integrate the equation. Integrate this equation with this boundary condition. At R equals to R1, concentration is XA1. At R equals to R2, concentration is XA2. So this is what this thing you will get actually. So so D XA by, so this will be a D XA by 1 minus XA will be equals to C1 divided by R raised to 2 plus N by 2 dr. Okay. So this will be N by 2 divided by this R square. This is what you will get, C1. Integrating this equation, you will be getting D XA by 1 minus XA will be equals to C1 R total raised to 2 plus N by 2. This is just N by 2. This is not, this is 2 or N by 2 plus 2. So this by 2 is just for N. So you can take out this constant, this is also constant, and this will be equals to C1. What will be equals to C1? R square 1 minus XA R raised to N by 2. So R square plus R raised to N by 2 will be N by 2 plus 2. So this will be a C1 divided by R. So again integrating this equation, ln 1 minus XA minus, that will be equals to minus 1 plus N by 2 C1 R 1 plus N by 2. This will be a R raised to, so integration of R raised to N will be a R raised to N minus 1 divided by N minus 1. That is what here, plus C2. Now we have two boundary conditions. Rearranging the equation. This is rearranging the equation. Just a rearrangement of this equation. Just bracket is kept put here. And this is multiplying it by minus 1. Here also I have minus 1. Here also I have minus 1. So this is 1 plus N by 2 into R raised to 1 plus N by 2. This is double integration. Now substituting. So here I have ln. Here I have ln. To avoid a non-linearity, a logarithmic term can be eliminated. This is exactly we have done in our previous problem. First case, to avoid this logarithm ln term, so this constant can be replaced by some other constant with ln. This constant can be replaced by some other constant with respect to ln. Why we are doing this? We are doing this to avoid the ln, so that we can have linear equation, and linear equation can have a easier mathematical manipulation as well as a solution. Okay, so substituting this, what you will get, 1 minus XA will be equals to K1 raised to 1 plus N by 2 R raised to 1 by 2, 1 by, okay, this raised to into K2. Now K1 and K2 can be estimated by using boundary condition. At R equals to R1, substitute R equals to R1, you will get XA equals to XA1. At R equals to R2, XA equals to XA2. Now this is what R equals to R1. Okay, R equals to R1 and R equals to R2. You will then subtracting that equation. So you will be getting K1. Not subtracting, dividing the equation. So 1 minus XA1 divided by 1 minus XA2. So K2 get cancelled. So this will be, this is what you will get. Using this, you can get the value of K1. This is the value of K1. This is value of K1. And now substituting this value of K1 here, any one of the equation, I can get a value of K2. This is the value of K2. This is value of K2. Now substituting value of K1 and K2, I will get a concentration profile. So this is my concentration profile, you can see. So this is my concentration profile. So you can see this concentration profile. So which will be equals to, so it involves variation of temperature, because, and in previous case, there was no variation of temperature. N was equals to, what was the N? N will be equals to 1 actually. So that is what previous concentration profile we got. So 1 minus R1 divided by 1 plus N by 2 minus 1 by R, 1 plus N by 2 whole divided by 1 R1, 1 plus N by 2 minus 1 upon R2, 1 plus N by 2. I'm using this at a given value of R. I can get a given value of concentration. This is my concentration profile. Now, how to get a flux profile for this actually? So this is what the flux profile is there actually. This is what flux profile is there. So dxa by dr, dxa by dr also you can use, or you can use K1 also. So this is what this whole term you can see. What is this? R n by 2, okay, R n by 2, and this 1 minus xa dxa by dr. This equals to C1, that is equals to K1, and this is ln actually. And this K1 is equals to this actually. Substituting this K1 value, I can get a flux actually. This is how I will get dxa by dr, dxa by dr. So this dxa by dr, I can substitute it here and get the flux profile. This is my flux profile, how flux is changing. So because flux is a function of R, that will not be there. Flux is constant, okay, which will be given. If total pressure is given and diffusivity at temperature T1 is given, so ideal gas constant, temperature T1, inner radius, outer radius, and this R square, okay, R square, it is inversely proportional, and 1 minus XA, 1 minus XA1. This will be a flux profile. Now, how to get a rate of evaporation? So this will be estimated at R equals to R2 and multiplied by surface area. Rate of mass transfer from the surface of the bubble. From the surface of the bubble. So this will be a mass fraction. This will be a 4 pi R1 square into NaZ. This will be a rate of evaporation of bubble. Mass transfer from the bubble. So that will be a surface area of the bubble multiplied by NaZ evaluated at R1. That will give me this will be a rate of mass transfer, or this will give me what will be the rate of evaporation of bubble, how long it will take to evaporate complete bubble. Using this, actually again you can consider a pseudo steady state, quasi steady state, and you can reduce the boundary from R equals to R1 to R equals to 0, and you can estimate what will be the time required to evaporate the bubble. This will give me a rate of evaporation. This is flux multiplied by surface area, and this surface area and flux estimated at R equals to R1. Flux estimated at R equals to R1, rearranging the equation, this will give me a rate of evaporation of bubble. Okay. Anybody has any confusion or any doubt over today's discussion? Just most importantly, I will repeat this second problem where there was a temperature variation and we have estimated a rate of evaporation of bubble also. What will be the rate of evaporation of A into P? Okay, so this temperature is varying with R, diffusivity is varying with temperature, and concentration is also varying with the temperature. So substituting this both here, so we'll be getting this equation and integrating this equation twice and eliminating ln term and calculating this K1 and K2, substituting this K1 and K2, this is what concentration profile we will get. And this is my flux profile. This is my flux profile. To calculate dxa by dr, so we'll take the help of C1. We'll take the help of C1, which is equals to minus ln K1. Minus ln K1, which will be equals to this, and substituting this ln K1 value, so I can get the value of dxa by dr and substitute this dxa by dr here. So dxa by dr here. So I will get this is the flux profile. This is the flux profile. I am calculating flux at R1. This will be flux estimated at R1 and this is the surface area at R1. So I will get here a mass transfer, rate of mass transfer of A in B. Is it okay? This is clear to everybody? Anybody has any doubt?